Procedural animation. If you're into game development, you have probably already heard of it before. It is a way of animating your characters where instead of baking keyframed motion into files using some animation software, you're using code to generate that motion in runtime. In simple words, you code a thing that animates itself. Pretty neat. The pros of this method are obvious. You can make your animations as adaptive to the surroundings as you want. This is especially great for larger walking creatures, where bare bones keyframe animations look really unmarketable. The downside of this, however, is the relative lack of artistic intent. Animation that is generated by code is significantly harder to tweak to get the exact look you want. But there is always the middle ground. Have a look here, for example. Have you noticed it? The character's feet are placed perfectly on the ground, while the rest of the body is clearly using keyframed animations that most likely came from motion capture. This is an example of a hybrid method, where procedural techniques are applied on top of traditional keyframe animations. This is the way procedural animation is most commonly used in the industry. In the game I'm making, I have a lot of these funny looking robots. I am not a terribly good animator, so creating motion that would look natural to them is basically out of the question. That is why I decided to animate them completely procedurally. And since I recently became fairly confident in my coding skills, we are going to build this as a very modular system, so it can be extensively reused in the future. Before we go really big with our ideas, let's have a look at the most basic of the examples. A four-legged spider, as I call it. Yeah, not terribly impressive, but everybody has to start somewhere. The spider has 5 distinct components, 1 body and 4 legs. Obviously, legs are meant to move the body, and the body, well, it's just here because what's the point of legs if you don't have anything to move? If you think about it, for each leg we only really care about the position of the foot, as the rest of the leg is going to be animated with inverse kinematics anyway. If you don't know what it is, if put extremely simply, it's an algorithm that makes a limb like this follow a point in space like this. Inverse kinematics is a pretty big topic that is worth its own video, so this is as far as I'm going to go into it today. What's important is that we only care about the foot of the leg, and we completely don't care about the rest. So, we have a body and legs that are meant to move it. That's good. But right now, it's just standing still. There isn't much for us to animate here. So, let's make it move in this direction. A simple way to implement it is to move the body in the direction you want and make the legs follow. You do it by checking the distance between the leg and some target location, which is attached to the body. And if the distance exceeds a certain value, you move the leg. Pretty simple. There is nothing inherently wrong with this method, but besides it being logically backwards, why is the body moving the legs? It is also non-realistic in terms of visuals. If you pay attention to how humans walk, you will notice that they bring their foot forward before placing it on the ground, while the body is catching up. Here we are basically doing it the opposite way, which becomes extremely obvious if the rig only has 2 legs. I don't like this. But what are we going to do then? Having these target locations attached to the body is extremely convenient, which is why I thought of this. Let's create another component that will carry leg target locations independently from the body. With that, we'll be able to easily initiate movement by just dragging this new component around, while the body is attached to the legs. Somehow. Everything makes perfect sense now. By the way, for some reason I decided to name this new component Core, which is not the best name for it objectively, but it has already stuck in my head, so deal with it. Now, we need to figure out how we are going to attach the body to the legs. Let's say we have a situation like this. Here is our spider, and here is the core. Basically, the core defines where we want our body to be located. To find a sensible location the legs can target, we'll first remember their initial offsets, the way they were positioned by the designer relative to the body. Then we will apply those offsets, but relative to the core this time. We should also do some raycasting to ensure that legs are grounded. Now, the sensible thing to do is to find the average of leg locations and put the body there. This, however, will result in the body lying on the ground, which isn't really what we want. That's why we will give legs a height parameter, which we are going to add to legs locations before finding the average. Now, if we calculate this parameter correctly, the body will be positioned nicely on the core. Great! If we calculate target locations like this, the spider will walk to the desired point and even move its body up and down while doing so. As you have probably already noticed, the walking animation isn't really well animated yet. Let's fix this. Imagine we have a timeline, 1 second long for example. This timeline will play every time the leg is moved. In the beginning, the leg has its starting location. If we press play, the time will start marching forward, and once we reach the end, we expect the leg to assume its target location. Pretty simple. First and the obvious idea is to just use linear interpolation to blend between the two locations. This is already looking much better. But in real life, creatures lift their legs from the ground while walking. To imitate this, we're going to add a curve. This curve will define the vertical offset of the leg during the animation. When calculating new leg position, we will sample this curve, multiply the value by the step height, and add it as a vertical offset to the linearly interpolated location. It's important that this curve stays in 0 to 1 range and also starts and ends with zeros. Additionally, we can replace linear interpolation with a curve too. This will make the motion feel significantly more organic. But that's not all there is to it. We can also control the step height based on the step length. And guess what we can use to achieve that? Yep, it's another curve. The idea here is that if you want to move further, you lift your leg higher. I know it isn't really true with humans, but it's a good enough estimation. Alright, now we already have a nice basic procedural animation rig for our full-legged spider. If we try to move the core, the machine will attempt following it to the best of its abilities. Actually, one could probably call this result good enough. But as you can see, there are some visual hiccups here and there, which will only become more apparent if the machine is piloted by an AI controller instead of an Xbox One. Long story short, we can make it look much better, but it's not going to be easy. Actually, the improvements in question are the reason I originally even decided to replace my old funky procedural animation code with an entire system, purposefully designed to get the most out of procedural animation. The problem we need to solve here is the lack of intention behind the thing's movement. As of right now, it is just following a point in space in the most straightforward way possible. It is not even trying to think of how it is supposed to reach it. It just moves there no matter what. Additionally, if we would want to introduce some more complex behavior, like stopping before turning or altering animations when the machine is idle instead of walking, all of that logic would have to go into our AI controller, basically the decision-making system. Imagine if to stand up from your chair, you'd have to make decisions to move each individual muscle in your body. That would be a nightmare to control. In programming, problems like this are usually solved by introducing a layer of abstraction. Oh, you're wondering what layer of abstraction means? Well, I'm glad you asked. Imagine you have some complex hardware, like a computer for example, and you want to run a simple program on it. If you were to interface directly with the hardware, your program would look something like this. This is machine code, by the way. And it would be damn near impossible to write. But thankfully, you have your trustful, or not so much, operating system and a programming language, which can interpret your abstract instructions, like print hello world, and translate them into low-level instructions, while also managing all the other subsystems that make your computer run. As a result, you easily write and run your simple program, while also getting the result you're expecting, without caring about how exactly your computer got it to work. In this case, operating system and programming language act as a layer of abstraction between the hardware and the end user. Pretty neat if you ask me. In our case, we want to introduce a layer of abstraction between the procedural animation rig and the decision-making system. But Kay, every rig is different. You can't know in advance what abstractions can be needed in every possible case, you might say. And you will be right. Rigs can be drastically different. One might be able to jump, another might not. One can have dozens of arms, while the other is a worm. Every rig needs a custom layer of abstraction. So, instead of creating a universal abstraction, I'll do the second best thing. Design tools that will allow us to somewhat easily create abstractions for each individual rig. I call this system intention driving. Basically, the role of the abstraction layer is played by one or multiple state machines, which control the rig by either changing parameters that affect all of the rig elements at once, or by addressing individual elements. The state machines can be interfaced with from anywhere outside the rig. They can be added, removed, swapped out, even in runtime, and can be reused for different rigs. For our full-act spider example, I have constructed an intention driver with 3 distinct states. Idle for when the machine is not moving, walking for when it is moving, and turning for when there is a significant change in rotation. So the machine stops, rotates in place, and then keeps moving. I have also introduced a few smaller features to the states, like, for example, returning legs into their resting positions after staying idle for long enough. You can also notice the machine becoming faster the longer it is in the walking state. As input, this intention driver just takes movement and turning values from sticks on my Xbox controller. Pretty neat. Alright, with this we already have some pretty decent looking animations, which we can easily control from outside the rig. What I want to do now is to add some more juice and detail. Look here, if I move the core, the body only follows it if the offset is big enough for legs to trigger a stepping motion. It would be way better if the body followed even the slightest of core's movements. Following the legs should move their bodies and not the other way around paradigm, I set out to solve the following problem. Remember that leg height parameter we added earlier? Basically, now we need to calculate it in runtime, so it corresponds to core's vertical location. And we also need to expand it in all 3 dimensions, so we can do horizontal offsetting too. We need to find such values x, y, and z for each individual leg that if added to legs' locations, the average location across all legs would match the core's location. This is actually a really simple task if we ignore the fact that we're working with legs. That means that assuming the x, y, and z values have no limitations, we can easily calculate them with a simple formula like this. But legs cannot extend indefinitely. They have limitations to their size, and generally speaking, each leg can have its own set of limitations. This is useful for creatures like headcrabs from Half-Life. As you can see, their rear legs are significantly smaller than the forward ones. Accounting the limitations, the solution of this problem really stretches out. This is only for a one-dimensional case, by the way, but in 3D it is really just the same thing but 3 times and with different values. I really don't want to explain all of this mess here, so if you're interested, I can probably make an additional short video about it. In any case, applying this solution, we get a very nicely looking result, which makes me happy. Also, all of this isn't really a solution. It is just an approximation of one, but it works well enough. Okie dokie, this simple at first glance, but complex if you look closer result, is what we're going to leave it at for today. There are a lot of things I didn't mention in this video, and even more cool things to come, like arms, wings, guns, complex bodies, etc, etc. All of that is to look forward to when I eventually end up developing it. Oh, and by the way, the name of the system is MPAS, Modular Procedural Animation System. I know, not very original, but it gets the job done. Alright, I'm going to be seeing you all next time. Bye bye. Start doing the flip. Jebediah Kerman is experiencing the views of his life, as you can see. Okay. Deploy the thing.
A King Martinit so good.
Oh, hell